Before we begin, take a moment to settle in. If you enjoy content that explores the mysteries of our world through science, curiosity, and calm discovery, consider liking this video, subscribing to the channel, and sharing it with someone who loves learning late at night. Your support helps this channel continue exploring the unknown. Now let's begin. The ocean covers more than 70% of our planet, yet we have explored only a fraction of it. When we look up at the night sky, we often feel awe at the vastness of space. But there is another vast, dark frontier much closer to us, one that begins just beyond the shoreline and descends into depths so extreme that sunlight has never reached them. These are the deepest places in the ocean, regions so remote and hostile that even our most advanced technology struggles to survive there. As we descend beneath the surface, the world changes quickly. Light fades, pressure increases, and the familiar sounds of the surface dissolve into something quieter, heavier, and more ancient. At just 200 meters down, sunlight begins to disappear. By 1,000 meters, darkness becomes nearly complete. And far below that, in the deepest trenches on Earth, the pressure is so intense it could crush steel like paper. The deepest known place in the ocean is the Challenger Deep, located in the Mariana Trench in the western Pacific Ocean. It reaches a depth of nearly 11 kilometers or about 7 miles beneath the surface. To put that into perspective, if Mount Everest were placed inside the trench, its peak would still be more than a mile underwater. This is a place where the pressure exceeds 1,000 times that of sea level, where temperatures hover just above freezing, and where life exists in forms unlike anything on land. Despite being discovered over a century ago, the Challenger Deep has been visited by humans only a handful of times. Even today, most of it remains unmapped in detail. Sonar gives us outlines and estimates, but the true shape of the trench, its caves, slopes, and hidden features, remain largely unknown. What makes these depths even more fascinating is that life thrives there. Strange, translucent creatures drift through the water. Microorganisms survive by feeding on chemicals leaking from the Earth's crust. Some animals produce their own light through bioluminescence, creating brief flashes in the darkness like distant stars. Yet for every confirmed discovery, there are unanswered questions. One of the greatest mysteries is how complex life survives under such immense pressure. According to our understanding of biology, extreme pressure should disrupt cellular processes, denature proteins, and prevent life as we know it. And yet, organisms not only survive but flourish. Some scientists believe these life forms may resemble some of the earliest organisms on Earth, offering a glimpse into how life began billions of years ago. As we move beyond the Mariana Trench, there are other deep regions just as mysterious. The Tonga Trench, the Kuril-Kamchatka Trench, and the Philippine Trench all plunge to depths where sunlight has never existed. Many of these places have never been directly observed by humans at all. We rely on unmanned submersibles, robotic explorers that send back grainy footage before being forced to retreat by crushing pressure or technical failure. And then there are the sounds. In the deep ocean, sound travels far. Over the years, underwater microphones called hydrophones have detected strange noises coming from the depths. Some are eventually explained as ice cracking, earthquakes, or whale calls distorted by distance. But others remain unexplained. One of the most famous is a sound known as the bloop, detected in the late 1990s. It was louder than any known biological sound and originated from deep in the Pacific Ocean. While scientists later suggested it may have been caused by ice movement, some researchers quietly admitted the sound was unusually powerful and did not perfectly match known ice-related patterns. This uncertainty has fueled speculation. Some theories suggest there may be large, undiscovered marine animals living far deeper than we once believed possible. Creatures adapted to pressure, darkness, and scarcity in ways we don't yet understand. While mainstream science remains cautious, it also acknowledges that the ocean still holds countless undiscovered species. Every deep-sea expedition finds new life forms, often completely unlike anything previously documented. Other theories go further into the realm of speculation and conspiracy. Some believe there are structures on the ocean floor, artificial shapes detected by sonar that resemble walls, roads, or even cities. Most scientists attribute these to natural geological formations, such as basalt columns or tectonic ridges. But the lack of direct visual confirmation leaves room for imagination. There are also persistent rumors of underwater bases, secret research facilities hidden in trenches too deep for conventional exploration. These ideas often stem from declassified military documents confirming that submarines routinely detect unidentified objects moving underwater at speeds far beyond known technology. These objects, sometimes called unidentified submerged phenomena or USPs, are acknowledged but unexplained. While there is no evidence that these objects are extraterrestrial or artificial, their behavior challenges our understanding of physics and engineering. Some scientists propose advanced drone technology. Others suggest sensor errors or misinterpretation of data. Still, the ocean keeps its silence. The deeper we go, the older the world becomes. In the abyssal plains and trenches, sediment accumulates incredibly slowly. In some places, a single centimeter of sediment may represent thousands of years. This means that deep ocean floors preserve a record of Earth's history stretching back millions of years, largely untouched by surface disturbances. Volcanic activity is also common in these regions. Hydrothermal vents release superheated, mineral-rich water into the ocean, creating ecosystems entirely independent of sunlight. These environments rely on chemosynthesis rather than photosynthesis, reshaping our understanding of what life requires to exist. Some scientists believe that studying these ecosystems may help us understand the possibility of life on other worlds, such as the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. In this way, the deepest parts of our own ocean may be the closest analog we have to alien environments. And yet, for all our technology, there are places we still cannot reach. Some trenches have unstable slopes that collapse without warning. Others contain pressures that exceed the design limits of even our strongest submersibles. Communication becomes difficult, navigation uncertain. At extreme depths, a single malfunction can mean permanent loss. There are parts of the ocean floor we have mapped in less detail than the surface of the moon. As you imagine these places, vast and silent beneath miles of water, it becomes clear how little we truly know about our own planet. The deep ocean is not just empty space. It is a living, shifting world shaped by forces older than humanity itself. And as we continue descending deeper into the darkness, there are still more mysteries waiting below. As we continue downward, past the deepest points ever reached by human-made machines, the ocean becomes less a place and more a condition. Here, depth is not measured only in meters but in isolation. There is no light, no familiar reference, no horizon. Just water, pressure, and time. In these depths, pressure increases by 1 atmosphere every 10 meters. At the bottom of the deepest trenches, this pressure exceeds 1,100 atmospheres. That is the equivalent of having the weight of a fully loaded commercial jet pressing down on a surface the size of a postage stamp. And yet, the water itself does not feel violent. It is still, slow, and heavy, pressing inward from every direction equally. This is one of the reasons the deep ocean feels so alien. On land, gravity pulls downward. In the abyss, pressure surrounds. There is no up or down in the way we understand it. Objects do not fall. They sink gently, sometimes taking days or weeks to reach the bottom. This slow rain of organic material from the surface is known as marine snow. Tiny fragments of dead plankton, waste, and microscopic debris drift down from above, feeding entire ecosystems that never see the sun. For many deep-sea creatures, this snow is the primary source of energy. Meals are rare, unpredictable, and often fiercely contested. Some animals have adapted by becoming nearly motionless, conserving energy for long periods. Others have evolved enormous mouths and expandable stomachs, allowing them to consume prey nearly their own size when the opportunity arises. In this environment, wasting energy can mean death. But there are places even deeper where marine snow barely reaches. These are the Hadal zones, named after Hades, the underworld of ancient mythology. These zones exist almost exclusively within deep ocean trenches, narrow scars in the Earth's crust formed by tectonic plates colliding and sliding beneath one another. The Hadal zone begins around 6,000 meters down and extends to the deepest points known. For a long time, scientists believed these zones were nearly lifeless. The conditions seemed too extreme, too hostile. But as exploration improved, life was found even here. Amphipods, snailfish, and microorganisms adapted to pressures that would instantly kill surface-dwelling species. One of the most remarkable discoveries was that some Hadal creatures contain special molecules in their cells that stabilize proteins under pressure. These molecules, called piezolites, help prevent cellular structures from collapsing. Without them, life at these depths would not be possible. Still, biology only explains part of the story. When sonar surveys scan the deep ocean floor, they sometimes reveal features that do not immediately make sense. Perfectly straight lines stretching for kilometers. Angular shapes that appear out of place in a world shaped by erosion and chaos. In most cases, geologists eventually identify these as fault lines, sediment waves, or volcanic formations shaped by immense pressure and time. But not all anomalies are easily explained. There have been instances where sonar detected massive objects rising from deep trenches and then disappearing just as quickly. Naval records, some of which have been partially declassified, describe submerged objects moving at speeds impossible for known submarines, without propulsion noise, and without disturbing surrounding water in expected ways. Official explanations usually cite sensor glitches or misinterpretation of data. But the consistency of some reports has kept speculation alive. One theory suggests these objects could be natural phenomena, perhaps large masses of superdense biological matter or unusual fluid dynamics occurring at extreme depths. Another proposes advanced human technology, developed in secret and tested far from observation. And then there are theories that venture further beyond conventional science. Some speculate that the deep ocean could host non-human intelligence, not extraterrestrial in the traditional sense, but something that evolved here long before humans ever walked upright. A civilization not bound to land or air, but to pressure and darkness. Mainstream science does not support this idea. There is no physical evidence of advanced underwater civilizations. And yet, the idea persists, partly because the ocean has always represented the unknown. It is vast, inaccessible, and capable of hiding almost anything. Throughout history, sailors reported encounters with massive shapes beneath their ships. Shadows moving faster than currents. Objects that followed vessels for miles before vanishing into the depths. While many of these accounts can be attributed to fear, fatigue, or known marine animals, not all are easily dismissed. Even today, modern sonar operators sometimes describe feeling uneasy when tracking deep-moving contacts that behave unpredictably. Not because they believe in monsters or hidden civilizations, but because the ocean does not always behave as models predict. Another enduring mystery lies in underwater caverns. Beneath the seafloor, especially near tectonic boundaries, there are vast networks of caves and tunnels carved by volcanic activity and chemical erosion. Some of these spaces are filled with superheated water, others with dense brine pools so salty that marine life floats above them as if suspended over invisible lakes. These brine pools are toxic to most organisms, yet some specialized bacteria thrive at their edges. The boundaries between normal seawater and brine are so sharp they appear like shimmering shorelines underwater. To early explorers, these places looked almost artificial, like submerged landscapes from another world. In some regions, sonar has detected voids beneath the seafloor far larger than expected, raising questions about the true structure of the ocean crust. While geologists explain these as magma chambers or collapsed lava tubes, their scale and complexity continue to surprise researchers. The deeper question is not whether we have explanations, but how incomplete those explanations still are. More than 80% of the ocean remains unmapped in high resolution. That means most of the planet's surface is still effectively unseen. We know more about the terrain of Mars than we do about large portions of our own seafloor. And as exploration technology improves, each new dive tends to raise more questions than answers. In recent years, deep-sea expeditions have discovered species that appear to challenge basic evolutionary assumptions. Some animals show extremely slow genetic change, remaining nearly identical to ancestors that lived millions of years ago. Others display rapid adaptation, evolving unique traits in isolation within individual trenches. This suggests that deep trenches act like biological islands, separated not by distance, but by pressure and depth. Life within them evolves independently, creating ecosystems that may be entirely unique to a single location on Earth. It also raises the possibility that some species may exist in only one trench in one narrow range of depth, completely unknown and extremely fragile. And still there are depths we cannot yet reach. Not because we lack curiosity, but because the environment actively resists us. Materials fatigue. Electronics fail. Navigation becomes unreliable. Even light itself behaves differently under such pressure, scattering in unfamiliar ways. Each descent into the deep is a reminder that the ocean is not empty space. It is a force, ancient and indifferent, shaped by gravity, heat, and time on scales far beyond human experience. As the surface world sleeps, waves rolling quietly against distant shores, the deepest parts of the ocean remain unchanged, dark, pressurized, and patient. And far below, in places no human eyes have ever seen, the Earth continues its slow, silent processes, waiting to be discovered. As we descend further into the unseen layers of the ocean, it becomes clear that depth is not a single boundary, but a gradual surrender of familiarity. The deeper we go, the less the rules of the surface apply. Physics still governs everything, but it expresses itself differently here, more quietly, more slowly. Temperature in the deep ocean is remarkably stable. No matter the season above, most of the abyss remains just a few degrees above freezing. This cold is not sharp or biting. It is constant, unchanging, and timeless. Combined with immense pressure, it creates an environment where chemical reactions slow, movement becomes deliberate, and decay happens at a pace almost unimaginable on land. This is one reason why objects that sink into the deep ocean can remain preserved for decades, even centuries. Shipwrecks resting miles beneath the surface often appear eerily intact. Paint remains visible. Letters are sometimes readable. Personal items lie undisturbed, as if time itself has been slowed. But preservation is selective. In the deepest zones, microorganisms still exist, and given enough time, they will consume almost anything organic. What remains are quiet outlines of human history, resting among creatures that evolved without any awareness of the world above. Some scientists believe the deep ocean may act as a kind of biological archive. Because conditions change so slowly, species here may preserve traits lost elsewhere on Earth. Studying them is like looking backward through evolutionary time, uncovering strategies life once relied upon when the planet itself was younger and harsher. Yet the ocean does not only preserve, it also erases. Entire geological features rise and collapse in silence. Submarine landslides, larger than anything that occurs on land, reshape the seafloor without warning. Mountains slump into trenches. Sediment clouds drift for hundreds of kilometers, eventually settling into new, unfamiliar patterns. These events rarely reach the surface. When they do, they may be felt as distant tsunamis, long after their true origin has been forgotten. In the deepest trenches, earthquakes are common. The immense stress of tectonic plates grinding against each other releases energy that travels through rock and water alike. Sometimes, this activity opens temporary fissures in the seafloor, releasing chemicals and heat from deep within the earth. These brief moments can create sudden blooms of life. Bacteria rapidly colonize new vents. Small animals follow, feeding on them. Entire ecosystems can appear, thrive, and disappear within a human lifetime, all without ever being seen. This constant creation and destruction raises an unsettling question. How much of the ocean's deepest life is transient, existing only for a short geological moment before vanishing completely? Some researchers believe that many species we will never discover have already lived and gone extinct in the deep ocean, leaving no trace we can detect. Evolution here may be faster and more experimental than we assume, shaped by isolation and extreme conditions. And then there is the question of sound again. At extreme depths, sound behaves strangely. Low-frequency waves can travel vast distances, bending with temperature layers and pressure gradients. A single sound event can echo across entire ocean basins, arriving at distant sensors hours or even days later. This is why some deep-sea sounds are so difficult to locate. By the time they are detected, they have already changed shape, stretched, and blended with other signals. Some hydrophone recordings capture rhythmic pulses, repeating at intervals too regular to be natural, yet too irregular to match known machinery. In official reports, these are often classified as biological or geological noise. But in private discussions, even experienced acousticians sometimes admit uncertainty. One possibility is that these sounds come from ice interacting with the seafloor in ways we don't fully understand. Another is that they are produced by unknown marine animals communicating across great distances. Deep-sea creatures may rely on sound far more than surface species, given the absence of light. And then there are ideas that are spoken of more quietly. Some suggest that the ocean itself may produce sounds as a byproduct of large-scale processes we have yet to identify. Pressure waves generated by mantle movement, resonances within massive underwater caverns, entire sections of the planet shifting in subtle rhythmic ways. If true, these sounds would not be signals in the traditional sense, but expressions of Earth's internal dynamics, translated into the medium of water. As exploration continues, researchers have begun to notice something else. The deep ocean does not seem as uniform as once believed. Chemical composition, temperature, and biological activity can vary significantly over surprisingly small distances. Two trenches of similar depth can host entirely different ecosystems. This suggests that each deep region is shaped by a unique combination of factors: local geology, water circulation, nutrient flow, and historical isolation. In effect, the deep ocean is not one world, but many overlapping worlds stacked vertically beneath the surface. This complexity makes exploration difficult. Tools designed for one trench may fail in another. Models that predict conditions in one region may not apply elsewhere. Each descent becomes an experiment, with unknown variables and unpredictable outcomes. It also means that assumptions can be dangerous. There was a time when scientists believed fish could not survive below a certain depth. That assumption was proven wrong. Later, it was thought that vertebrates could not live in the Hadal Zone. That too was overturned with the discovery of deep-dwelling snailfish. Each boundary we define seems temporary. This pattern has led some thinkers to wonder whether there are limits we have not yet challenged. Depths at which life transitions into forms so unfamiliar that we fail to recognize them as life at all. Systems that operate on principles we have not yet identified. While such ideas remain speculative, they highlight a deeper truth. Our understanding of the ocean is shaped by our tools, our definitions, and our expectations. Change any one of those and the picture shifts. The deep ocean does not reveal itself easily. It does not reward haste. It does not respond to curiosity alone. It requires patience, resilience, and acceptance of uncertainty. And so, as we continue to descend in thought, into waters untouched by exploration, it becomes clear that the deepest places in the ocean are not just far away. They are conceptually distant. They challenge how we think about life, about time, and about our place on this planet. Below us, the pressure increases. The darkness thickens. And the unknown becomes not something to fear, but something vast, quiet, and waiting. As the descent continues, imagination begins to slow, not because there is less to consider, but because the scale of what lies below becomes difficult to hold all at once. The deep ocean does not announce itself with drama. It unfolds gradually, layer by layer, asking for patience rather than urgency. At extreme depths, even movement becomes rare. Currents that dominate surface waters weaken, replaced by slow, almost imperceptible flows driven by differences in temperature and salinity. Some deep water masses have been isolated from the surface for thousands of years. The water surrounding certain trenches may have last touched the atmosphere before human civilization existed. This isolation has consequences. Oxygen levels can be extremely low, forcing organisms to evolve highly efficient respiratory systems or abandon oxygen altogether. Some microbes rely on sulfur, methane, or hydrogen instead, drawing energy from chemical reactions that would be toxic to most surface life. These processes blur the line between biology and geology, life and environment becoming inseparable. In these depths, the distinction between living and non-living can feel less clear. Bacterial mats grow over rocks like living skin. Mineral formations resemble organic structures. Life clings to heat, pressure, and chemistry rather than light. One of the most surprising discoveries in recent decades is the presence of microplastics in the deepest parts of the ocean. Even in trenches miles below the surface, traces of human activity have arrived, carried down slowly over years. Fibers, fragments, and particles settle alongside marine snow, becoming part of the deep ecosystem. This realization has shifted how scientists think about remoteness. There may be places we cannot reach physically, but there are no places completely untouched. The deep ocean is connected to the surface in subtle, persistent ways. Yet despite this connection, the deep remains largely autonomous. When equipment fails in the abyss, there is no rescue. Submersibles lost to pressure implosion vanish instantly, leaving little more than scattered debris. Communication cables snapped by underwater landslides can take months to locate and repair. In some cases, the cause is never fully identified. There have been moments when remotely operated vehicles abruptly lost signal near the seafloor, only to be found later intact, as if something had interfered and then released them. Engineers typically attribute this to technical malfunction or interference from terrain. But such events contribute to the sense that the deep ocean does not always behave as expected. In the realm of speculation, some suggest that electromagnetic anomalies may exist near certain trenches. Variations in Earth's magnetic field, combined with pressure and mineral composition, could potentially disrupt instruments in ways we do not yet understand. These effects are subtle, difficult to measure, and easy to dismiss, but they are not impossible. What is certain is that our instruments are designed with assumptions based on surface conditions. Every time we push them beyond those assumptions, we encounter surprises. There is also the matter of scale. The largest mountain range on Earth is not on land. It is underwater. The mid-ocean ridge system stretches across the planet like a seam, longer than any terrestrial mountain chain. Much of it lies thousands of meters below the surface, unseen and unmapped. Where this ridge intersects with trenches and fracture zones, the seafloor becomes extraordinarily complex. Valleys, peaks, and plateaus interlock in ways that defy simple explanation. These regions may host conditions unlike anywhere else on Earth, yet they remain among the least explored. Some scientists believe that entire categories of geological processes occur primarily underwater, hidden from observation. Processes that shape continents over millions of years without ever breaking the surface. In this view, the ocean floor is not a passive backdrop, but an active engine of planetary change. And still there are gaps. There are places where sonar returns nothing clear, as if the signal is absorbed or scattered unpredictably. These zones are often chalked up to technical limitations or unusual terrain. But the repetition of such anomalies has prompted deeper investigation. In rare cases, follow-up surveys yield different results. suggesting that the seafloor itself may change more rapidly than expected. Sediment shifts, slopes collapse. Features appear and disappear between scans. This dynamism challenges the idea of the deep ocean as static. It is not frozen in time. It is slow, yes, but it is always moving. From a human perspective, this movement feels almost peaceful. Changes happen on timescales longer than attention spans. But from a geological perspective, the deep ocean is restless. The idea that something could exist there unnoticed for long periods is not unreasonable. Not something extraordinary necessarily, but something simply unobserved. A process, a species, a pattern. Throughout the history of science, the unknown has often been mistaken for the impossible. The deep ocean has repeatedly shown that assumptions based on limited data do not hold under pressure. As technology advances, new methods of exploration are being developed. Autonomous vehicles capable of long-duration missions. Sensors that can withstand extreme pressure. Artificial intelligence systems that analyze sonar data for subtle patterns humans might miss. Each new tool brings us closer, but also reveals how much remains beyond reach. There is a quiet humility that comes from studying the deep ocean. It reminds us that intelligence does not equal control, and knowledge does not equal dominance. Some environments cannot be mastered, only approached carefully. And perhaps that is part of their value. As the surface world moves quickly, driven by noise, light, and constant change, the deepest places on Earth remain slow, dark, and patient. They operate on principles older than civilization, older than mammals, older than complex life itself. They are not waiting for us. They do not need us. But they offer perspective simply by existing. Far below the waves, where pressure reigns and time stretches, the ocean continues its quiet work. And with each descent, physical or imagined, we come to understand not just how deep the ocean is, but how deep our curiosity can go. As we move even deeper into this quiet descent, the concept of distance begins to lose its meaning. In the deep ocean, separation is not measured in miles, but in layers of pressure, chemistry, and isolation. Two places may be close on a map, yet entirely disconnected in reality, divided by invisible boundaries that life and technology struggle to cross. One such boundary is the thermocline, a layer where temperature changes rapidly with depth. Below it, water becomes colder and denser, sinking slowly and carrying dissolved gases with it. Over long periods of time, this circulation shapes the deep ocean, delivering oxygen to some regions while leaving others starved of it. In oxygen-poor zones, life adapts in ways that seem almost counterintuitive. Some organisms slow their metabolism to an extreme degree. Others rely on symbiotic relationships, sharing resources at a microscopic level. Entire communities exist in balance so delicate that a slight change in chemistry could cause them to collapse. This fragility is one reason deep-sea ecosystems are difficult to study. Introducing light, sound, or movement can disrupt behaviors that evolved in total darkness. Some creatures flee instantly. Others freeze, overwhelmed by stimuli they have never encountered before. There have been moments when submersible cameras captured animals that appeared curious, approaching slowly, then retreating just as gently. These encounters feel almost intimate, brief meetings between worlds that rarely intersect. Yet curiosity is not universal. Some deep-sea animals react with sudden aggression when disturbed, not out of malice but instinct. In an environment where energy is scarce, competition can be intense. Any intrusion is evaluated as either threat or opportunity. This brings us to one of the more persistent ideas surrounding the deep ocean, that it may hide predators far larger than any yet known. From a biological standpoint, there are limits to size in deep environments. Food scarcity makes sustaining massive bodies difficult. And yet, the discovery of giant squid, once thought mythical, reminds us that rarity does not mean impossibility. Giant squid were known only from legends and fragments until relatively recently. Even now, live footage is rare. They inhabit deep waters, surfacing only occasionally, and grow to sizes that once seemed impossible. Their existence reshaped scientific caution. If such large, complex animals could remain hidden for so long, what else might exist beyond our limited observation? Most scientists would say that truly enormous undiscovered animals are unlikely. But unlikely is not the same as impossible. This uncertainty has fueled stories of deep-sea leviathans, ancient creatures adapted to pressure and darkness, surfacing only rarely. While these stories remain firmly in the realm of speculation, they persist because the deep ocean leaves space for them. And space, when combined with darkness, invites imagination. There is also the matter of time perception. In the deep ocean, cycles are slower. There is no day or night. No seasons in the way we experience them. Some deep-sea animals may live for decades, even centuries, with growth so gradual it is barely detectable. This longevity changes how life interacts with its environment. Reproduction may be infrequent. Movement may be minimal. Survival depends on patience rather than speed. In such a world, sudden change is catastrophic. When disturbances occur, whether from natural events or human activity, recovery can take generations. This has led some scientists to warn that damage to deep-sea environments may be effectively permanent on human timescales. Mining interests have already begun to explore the possibility of extracting minerals from the deep ocean floor. Polymetallic nodules, rich in rare metals, lie scattered across vast abyssal plains. They formed over millions of years, growing millimeter by millimeter. Removing them would be easy. Replacing them would be impossible. The debate surrounding deep-sea mining highlights a broader question. How should we treat places we barely understand? The deep ocean challenges our sense of responsibility because its consequences unfold far from view. And then there are the trenches again. Some trenches appear to trap debris, concentrating organic material and pollutants alike. This has led to the discovery of unusually high levels of contamination in hadal organisms, despite their isolation. Chemicals sink, accumulate, and persist. This accumulation raises another unsettling possibility. The deep ocean may act as a long-term sink for the byproducts of civilization, quietly storing evidence of human activity long after the surface has changed. In this way, the deepest places on Earth may become a record not only of natural history, but of human presence as well. Still, the ocean remains largely indifferent. It does not respond to our concerns. It does not adapt to our schedules. It simply continues, governed by forces far older than policy or intention. As exploration continues, some researchers have proposed a shift in perspective. Instead of trying to conquer the deep, we should learn to listen to it, to observe without interference, to accept that some questions may remain unanswered. This idea runs counter to the traditional narrative of exploration, which celebrates discovery and mastery. But the deep ocean offers a different lesson. That understanding does not always require access. That mystery can coexist with knowledge. In the darkness below, there is no urgency, no demand, only depth. And as our thoughts continue to drift downward, following the contours of trenches and plains unseen, we are reminded that the deepest places in the ocean are not just remote. They are reflective. They mirror our limits, our curiosity, and our willingness to sit with the unknown. As the descent continues, attention naturally shifts from what we expect to find, to what we may never fully understand. The deepest parts of the ocean are not defined by dramatic events, but by persistence. Pressure that never relents. Darkness that never lifts. Silence broken only by distant, distorted sound. In such an environment, even the concept of exploration changes. There is no wide field of view. No sweeping landscape. Everything appears in fragments. A few meters illuminated by artificial light, surrounded by blackness that absorbs all context. It is easy to forget how small that illuminated space truly is compared to what surrounds it. This limitation shapes perception. When cameras capture something unfamiliar in the deep ocean, interpretation becomes difficult. A shape may appear massive or small depending on distance. Movement may seem deliberate or random depending on current and perspective. Without reference points, certainty is elusive. This is one reason deep-sea footage sometimes feels unsettling. Not because it shows danger, but because it denies clarity. There have been moments when explorers reviewing recordings noticed shapes moving at the edge of the frame, just beyond the reach of light. Most are dismissed as debris, shadows, or marine life passing quickly. But the fact that they cannot be immediately identified highlights how little context we have at those depths. In science, uncertainty is not a flaw. It is a signal. It points toward questions that have not yet been answered, rather than conclusions that should be feared. And in the deep ocean, uncertainty is the default state. Even mapping is an exercise in approximation. Sonar sends sound waves downward and interprets their return. But sound can reflect, refract, and scatter in complex ways, especially near steep terrain. What appears as a smooth slope may hide deep fissures. What looks like a solid wall may be layered and fragile. This means that much of what we think we know about the deepest ocean floor exists as probability rather than certainty. Some researchers have begun experimenting with new approaches, combining sonar with gravitational measurements and chemical sampling to infer structures that cannot be directly observed. These methods are promising but still limited. There remains a fundamental barrier. Water absorbs energy. It isolates. It separates. And yet, life adapts. One of the most remarkable aspects of deep-sea biology is not its strangeness, but its efficiency. Nothing is wasted. Structures are minimized. Functions overlap. Eyes may disappear entirely, replaced by sensitivity to vibration or chemical gradients. Some deep-sea organisms do not move at all for long periods. They wait. In a world where food arrives unpredictably, patience is survival. This patience extends beyond individual organisms. Entire ecosystems operate at a pace that feels almost static. Growth measured in millimeters per year. Population changes unfolding over centuries. From the surface, such systems might appear inactive. But they are not. They are simply tuned to a different rhythm. It is tempting to project human narratives onto these places, to imagine hidden threats or ancient secrets. But often, the most extraordinary thing about the deep ocean is its restraint. It does not erupt constantly. It does not reveal itself easily. It remains. Still, imagination persists. Some theories propose that the deep ocean could hide relics of Earth's distant past. Not artifacts in the human sense, but structures formed when the planet was younger. When tectonic activity was more intense. When chemistry and heat interacted differently. Submerged plateaus and ridges may preserve conditions no longer found anywhere else. In this sense, the deep ocean is not just remote, but ancient. Others wonder whether the ocean floor could conceal evidence of events that reshaped the planet, such as massive impacts or extinct volcanic systems, their traces erased from land but preserved beneath miles of water. These ideas are grounded in geology, not fantasy. But because access is limited, confirmation remains difficult. And then there are the ideas that step beyond geology. Some suggest that consciousness itself may not be as bound to surface conditions as we assume. That intelligence could emerge in forms we do not recognize, shaped by pressure rather than light, by sound rather than sight. Science does not currently support this. There is no evidence of non-biological intelligence in the deep ocean. But the question itself reflects something important. The deep ocean challenges our definitions. What counts as life? What counts as awareness? What counts as presence? When environments differ so radically from our own, assumptions weaken. Categories blur. This does not mean anything is possible. But it does mean that our understanding is provisional. The ocean teaches this lesson repeatedly. Every time a boundary is declared, it is eventually crossed. Every time a limit is assumed, it is tested. And yet progress is slow. Funding for deep-sea research is limited. Missions are expensive. Risks are high. Much of what we know comes from brief windows of observation, not continuous study. This makes the deep ocean one of the last places where mystery remains not by design, but by circumstance. And perhaps that is why it continues to capture attention. In a world where satellites map every corner of land, where data flows constantly, the deep ocean offers something rare. A space where not knowing is normal, where silence is meaningful, where darkness is not absence but context. As thoughts drift downward, deeper into trenches and along unseen slopes, there is no conclusion waiting, no final revelation, only depth. And in that depth, a reminder that exploration does not always require arrival. Sometimes, it is enough to descend slowly, to observe quietly, and to let the unknown remain what it is. As we continue this slow descent, the deep ocean begins to feel less like a destination and more like a state of being. It is a place defined not by landmarks, but by conditions that persist without interruption. Pressure that never eases, darkness that never breaks. A quiet so complete it feels almost physical. In these depths, even memory behaves differently. There are no daily cycles to mark time. No sunrise or sunset. For organisms that live here, the concept of a day may be meaningless. Life unfolds as a continuous present, shaped only by rare events and gradual change. This absence of rhythm affects behavior. Many deep-sea animals do not follow predictable patterns. They respond instead to subtle cues, a faint vibration, a distant chemical trace, a slight shift in water movement. These signals may be all that separates opportunity from starvation. To survive here is to be attentive without being active. This stillness has led some researchers to describe the deep ocean as meditative in nature. Not because it is peaceful in a human sense, but because it demands focus without urgency. Nothing happens quickly. Everything matters. As technology descends into these regions, it must adapt to this pace. High-speed exploration fails. Instruments designed for rapid data collection often miss what unfolds slowly. Some of the most valuable observations come from long-term sensors left in place for months or years, quietly recording changes too subtle for short missions to detect. These long-duration studies have revealed something unexpected. The deep ocean is not as uniform as once believed. It pulses, not dramatically but gently. Tiny fluctuations in temperature, pressure, and chemistry move through deep water masses like slow breaths. These pulses may be linked to surface weather, distant storms, or shifts in global circulation. Even the deepest trenches are not entirely isolated from the rest of the planet. This connection suggests that the deep ocean plays a larger role in Earth's systems than previously understood. It acts as a reservoir for heat, carbon, and nutrients, moderating climate over long timescales. Changes here may take centuries to become visible, but when they do, their effects can be global. Understanding this role is difficult, precisely because of the deep ocean's inaccessibility. We cannot easily observe cause and effect. We infer, model, and wait. This waiting is a recurring theme. In the deep ocean, waiting is not passive. It is adaptive. It is how life persists, how systems stabilize, how complexity emerges without chaos. This perspective reframes mystery. The unknown is not a gap to be filled immediately, but a space to be respected. And yet, there are moments when the deep does reveal itself. Occasionally, something rises from the depths. A deep-sea fish caught unexpectedly in shallower waters. A chemical plume detected far from any known source. A sound recorded that does not match any established pattern. These moments are rare, but they are reminders that the deep ocean is not sealed away. It interacts. It responds. Sometimes it surprises. There have been instances where researchers encountered species thought to be extinct, living quietly at depths where conditions remained stable long after surface environments changed. These so-called living fossils are not remnants of a frozen past, but survivors of continuity. Their existence challenges the idea that progress always moves forward. Sometimes survival means staying the same. This idea extends beyond biology. The deep ocean itself is conservative. It resists change. It absorbs disturbance slowly and releases it slowly. In a rapidly changing world, this stability is both comforting and concerning. Comforting because it suggests resilience. Concerning because when change does reach these depths, it may be irreversible. This duality adds weight to the question of exploration. To observe is to interfere. To illuminate is to alter. Even light, harmless on the surface, can disorient deep-sea organisms that evolved without it. Some researchers now experiment with red or infrared lighting, attempting to minimize impact. Others advocate for non-visual sensing entirely, relying on sound and chemistry rather than sight. These efforts reflect a growing awareness that the deep ocean is not just unknown but vulnerable. And yet it endures. Long after surface civilizations rise and fall, the trenches will remain. Long after languages change and borders disappear, pressure and darkness will persist. In this sense, the deepest places in the ocean offer perspective not through spectacle, but through endurance. They remind us that not everything needs to be seen to matter. Not everything needs to be understood to exist. Some truths are slow, quiet, and deep. As thoughts continue to drift downward, deeper than light, deeper than sound, deeper than certainty, there is no need to rush. The ocean does not. And so we continue descending not toward an answer, but toward a deeper appreciation of the vast, patient world beneath us. And as we remain in this downward drift, it becomes easier to understand why the deep ocean has always resisted being fully known. Not because it hides itself deliberately, but because it operates on scales that do not align with human urgency. In the deepest places, change is subtle. Movement is slow. Signals are faint. To notice anything at all requires patience measured not in minutes or hours, but in years, sometimes decades. This is why so many discoveries in the deep ocean are accidental. A sensor placed for one purpose records something unexpected. A survey meant to map terrain detects life instead. A malfunction reveals a pattern no one was looking for. Discovery here is rarely dramatic. It arrives quietly. One of the more humbling realizations to come from deep-sea research is how often we misinterpret absence as emptiness. Where we see nothing, there is often simply something operating below our threshold of detection. This is especially true at extreme depths, where life may be sparse, dispersed, and nearly motionless. Not because it is struggling, but because it has optimized itself for scarcity. In these environments, survival does not reward speed or strength. It rewards restraint. This principle applies beyond biology. Geological processes in the deep ocean are also restrained. Massive forces are at work, but they unfold slowly. Plates grind past one another at the pace fingernails grow. Heat migrates upward molecule by molecule. Pressure reshapes rock over spans longer than recorded history. From the surface, these processes are invisible, but they are constant. Some scientists have suggested that the deep ocean represents the closest thing Earth has to permanence. Not permanence in the sense of being unchanging, but in the sense of continuity. While continents shift and climates fluctuate, the deepest trenches remain cold, dark, and pressurized. They persist through ice ages and warm periods alike. This continuity has led to a subtle but profound shift in how researchers think about the deep ocean. It is no longer viewed simply as an extreme environment, but as a stabilizing one. A place where extremes cancel out rather than amplify. In a strange way, the deepest places on Earth may be among the most consistent. This does not make them safe. It makes them demanding. Human technology can visit these depths only briefly. Machines descend, observe, and retreat. They cannot linger indefinitely. They cannot adapt the way life does. Every mission into the Hadal Zone is temporary by necessity. And yet, even these brief visits have changed how we understand our planet. They have shown us that life does not need sunlight. that ecosystems can exist entirely on chemistry and heat, that isolation does not imply simplicity, that pressure does not eliminate complexity. They have also shown us that the unknown does not shrink as knowledge expands. It simply changes shape. As we learn more about the deep ocean, new questions replace old ones. Why do certain trenches host more life than others of similar depth? How do organisms migrate between isolated deep regions, if at all? What triggers sudden changes in deep ecosystems that otherwise remain stable for centuries? These questions do not have quick answers. And perhaps that is appropriate. The deep ocean teaches a different relationship with curiosity. One that values patience over resolution. One that accepts that some mysteries are not meant to be solved quickly, if at all. This perspective can feel unfamiliar. We are used to progress being visible, measurable, immediate. But in the deep, progress looks like listening longer, measuring more carefully, interpreting with humility. There is also something quietly reassuring about this. In a world that often feels crowded, mapped, and accounted for, the deep ocean remains vast enough to resist complete understanding. Not because it is hostile, but because it exists on its own terms. It does not rush to meet us halfway. And maybe that is why, even without dramatic discoveries or definitive answers, people continue to be drawn to it. To stories of trenches, pressure, darkness, and silence. The deep ocean reminds us that mystery is not a problem to be solved, but a condition to be experienced. Far below the surface, long after storms have passed and cities have gone quiet, the ocean continues exactly as it has for millions of years. Water pressing against rock, heat rising slowly, life adapting in ways we barely perceive. No audience, no witness required, just depth. And as this descent comes gently to an end, there is no need to surface suddenly. No need to resolve every question. The ocean does not. It remains below, vast and patient, holding its secrets not out of secrecy but out of scale, waiting not for discovery but for understanding. And whenever curiosity drifts downward again, the deep will still be there,